Hi all. In last class, we have discussed about aromaticity and we have seen what is aromatic, anti-aromatic and non-aromatic compounds are. If a system is cyclic planar conjugated and it is containing 4n plus 2 pi electron, it is called aromatic. And if a system is cyclic planar conjugated and it is containing 4n pi electron, then it is called anti-aromatic. Then we have seen what is non-aromatic is. Then after that, we have discussed the aromaticity of different anilines and we have determined the aromaticity of different compounds. And in last class, we have defined what is homoaromatic also. In today's class, we will start our discussion with quasi-aromatic compounds. The quasi-aromatic compound is a non-polar compound and it will have a double bond. And this molecule, by breaking the double bond, it will become polar compound because now the polar compound is an aromatic compound and we told the aromatic is the most stable compound. So a non-polar compound, by breaking a pi bond, it will become a polar compound and aromatic compound. And this aromatic compound will now have high dipole moment because in polar compound there will be charge, right? There will be positive and negative charge. So this will lead to the high dipole moment of the molecule. And we'll see some example. If you are looking at this molecule in this way, this molecule is not polar, but there is a chance of this pi bond to break. Suppose there's two possibility for this pi bond to break. Either it can break this way. In that case, it will form a structure like this. There will be negative charge here, positive charge here. And there is one more possibility. Suppose this bond is breaking here. In that case, what will happen? If this bond is moving here, then a negative charge will be here. So in second structure, a negative charge will come here and a positive charge will come here. Okay. So if you are looking at both one and this is first structure and the second structure. If you are looking at both one and two in one, this part is, as we already seen, it is aromatic and this part also aromatic. And in the second structure, this part, it is anti-aromatic and this part, as we already seen, it is also anti-aromatic. Okay. So there is two ways for this bond to break, but the second structure will never form because here both anti-aromatic structures are forming. So second structure will never form. But instead, from this molecule, the first structure can form because here the molecule is not at all polar, but from this to this, here we have two aromatic system in our molecule now. This also aromatic and this also aromatic. It will lead to the high stability of the molecule. That way, the molecule will exist in this way. The molecule exists in the form of the first molecule. While comparing both the neutral molecule and the first molecule, here there is no charge, so there is zero dipole moment. But in the first molecule, here we can see positive and negative charge. That means there will be a dipole moment. So compared to first molecule, there will be high dipole moment. Okay. So this is a quasi-aromatic molecule. Initially, it was not polar molecule, but a pi bond will break and a polar molecule will form. And this polar molecule is aromatic due to the high stability of this. It will remain in this way and it will induce a high dipole moment for the molecule. Okay. Now we'll take this example. Here also, we are looking at this molecule. This molecule is not polar, but there is a C double bond of bond is here. That means this bond can only break in this way because oxygen is a most electronegative atom. So if a bond is breaking, which is attached to oxygen, that bond should break towards the oxygen. Okay. So from this molecule, we'll get, from this molecule, we'll get a structure like this. Here we will get a negative charge, here we will get a positive charge. Again, while comparing the initial molecule, it is not polar, so it is having zero dipole moment. But our product, now there is a charge separation, that means there is a dipole moment. So compared to the first molecule, there will be dipole moment present in our molecule. Okay. Now look at this molecule. Here, there is a chance for this pi bond to break. And there is two possibility because in both end carbon atoms are present. So there is two chances. Either this bond can break here or this bond can break here. Okay. So we'll draw the product of both possibility. So in first, the bond is breaking towards above carbon. So here negative charge will come here, positive charge will come here. And we'll consider second possibility also. Suppose this bond is breaking towards this, then negative charge will come here, positive charge will come here. Now we have to see both first and second and determine which will form. If you are looking at first molecule, here it is a 1, 2, 3, 4, 5, 6, 7. It is a 7-membered ring, 3 pi bond and 1 negative charge. We already named this system as tropylium anion, and we have seen that tropylium anion is a non-aromatic system. Okay. Now here if we are looking, this we know it is a 5-membered ring with 2 pi bond and 1 positive charge. This we have already seen. It is an anti-aromatic system. Okay. Now we look at the structure too. In second molecule, this part, it is a 7-membered ring having 3 pi bonds and 1 positive charge. This is a tropylium cation. Tropylium cation is aromatic. This part, it is a 5-membered ring with 2 pi bond and 1 negative charge. Again, this also aromatic. So from this neutral molecule, only second molecule will form because here both parts are aromatic. So it will give high stability for the molecule. So again, initially it was 0 dipole moment present in the molecule. So after bond breaking, there will be a dipole moment compared to the initial molecule. Okay. So this is a quasi-aromatic molecule. Now we'll talk about this molecule. Here also we can see a double bond here. Again, there is 2 possibilities for this double bond to break because both ends are carbon. When we have a double bond, when one end is attached to oxygen and one end is attached to carbon, then there is only one possibility for the bond to break. This will move towards oxygen and you will get a structure like this. But if you have a double bond, when both atoms are carbon atom, there is 2 possibilities. Either this bond can break like this. This is the first possibility, or it can break like this. It is a second possibility. So we have to consider both possibility here. Suppose our bond is breaking this way, then a negative charge will come here, a positive charge will come here. And suppose the bond is breaking this way, in that case, a negative charge will come here, a positive charge will come here. Okay. Now we have to determine the aromaticity of both parts. First, we look at number 1, then we look at number 2. So in first molecule, if you are looking at this part, in boron, there is an unhybridized p orbital present, which is taking part in the delocalization. Now total number of pi electron which is present in the system is 2, 4, 6. So total 6 electrons are participating. It is completely delocalized. So that means this part is aromatic. Now if you are looking this part, again, there's a lone pair which is present on the oxygen, which can take part in delocalization. So total number of electrons that is present from these 2 pi bond and one of the lone pair on oxygen, 2 pi bond and 1 lone pair. So it will be 4 plus 2. So it will be total 6 electron. Again, this is also aromatic. Here both parts are aromatic. Now if you are looking here, in boron 1 p orbital is present. Here if you are counting total number of electrons here, 2 pi bonds are only participating. That means from 2 pi bond total 4 electrons. So a 4 electron means it is a anti-aromatic system. If you are looking at the second part, that is this part, here we can see 1 negative charge and 2 pi bond. That 2 pi bond and plus 1 negative charge. And here we can see 1 oxygen which is sp3 hybridized. For this oxygen to become sp2 hybridized, this lone pair on the oxygen should take part in the conjugation. In that case, 1 lone pair on the oxygen will also come. So total from 2 pi electron, it will come 4 electron. From 1 negative charge, 2 electron will come. From 1 lone pair of oxygen, again 2 electron will come. So total it will become 8 electrons. So again it will become anti-aromatic. So here both parts are anti-aromatic. Here both parts are aromatic. So from this molecule only first structure will form. Okay. So this is the quasi-aromatic molecule. Initially, there is a non-polar compound and there is a double bond in this molecule. If this double bond broken in certain way, we will get an aromatic compound which is more stable. So from this non-polar compound, we will get a polar compound. And this type of molecule is called quasi-aromatic molecules. Okay. So now you'll see the NMR of aromatic compounds. Now we'll see what will happen to the NMR of aromatic compound. NMR in detailed manner we'll discuss in some other class. In this class, you'll just see what will happen to the NMR of a aromatic and anti-aromatic compound. Okay. So in proton NMR, normally the ppm scale will be ranging from 0 to 10. In 0, we'll say shielded region, and 10 will say de-shielded region. Okay. Suppose we have an aromatic compound. Suppose this is our aromatic molecule here, and we are putting this molecule in NMR machine that we are giving a magnetic field B0. Due to the aromaticity of this molecule, there will be a ring current in the molecule. Due to the ring current in the molecule, there will be induced magnetic field in the molecule, which will be having the direction like this. So outside the ring, it will be having the same direction as of the applied field, but inside the ring, it will be having the opposite direction. Like this, outside it will be having the same direction as of applied field, but inside it will be having the opposite direction of the applied field. And suppose we have proton outside the ring and inside the ring also. For the outside, de-shielding will happen. And the proton that is inside the ring, shielding will happen. Because here both the induced magnetic field and applied magnetic field are opposite direction, but outside both are in the same direction. So that's why de-shielding will happen for the outside proton and shielding will happen the inside proton. So you just have to remember one thing. Suppose we have an aromatic system and there is proton present in both inside and outside the ring. For outside rings, shielding will happen. That means it will come close to 10, and inside proton, shielding will happen. That means it will come close to 0. Okay. Otherwise, if you have an aromatic system, outside proton will have high value, that high ppm value. Inside proton will have low value, that is low ppm value. You just have to remember this. You have to just remember the aromatic case, and you need to take the opposite in case of anti-aromatic. You don't have to remember about this ring current and all. You just have to remember, suppose if you have aromatic system and there is hydrogen present in both outside the ring and inside the ring. Outside the ring, it will be having high ppm. Inside the ring, it will having low ppm. In case of anti-aromatic, exactly the opposite case will happen. Suppose here also a proton is present inside the ring and outside the ring. Here, the opposite of this. That means inside the ring, high ppm will happen and outside proton will have low ppm. In exam point of view, we just have to remember, in case of aromatic, outside proton will have high ppm and inside proton will have low ppm. In case of anti-aromatic, outside proton will have low ppm and inside proton will have high ppm. Okay. This only you have to remember in this NMR of aromatic and anti-aromatic compound. For this, we'll take an example. We already discussed when we are discussing the anilines. We have seen that 18 aniline is aromatic. Right? Here. So what I told in case of aromatic, outside proton will have high value, that is high ppm. Inside proton will have low value, that is low ppm. Here 18 aniline is aromatic. Here this molecule have proton like this. It will be pointing towards the outside of the molecule. This all proton, and this molecule is also having proton which is pointing towards the inside part of ring. And these all protons are towards the inside part of ring. So what we have seen in case of aromatic, outside proton will have high ppm. So outside proton is having high ppm. In this case, it will having a 9 ppm. And inside proton will have low ppm. In this case, it is having a ppm of minus 3 ppm. Okay. This is due to the ring current and induced magnetic field in this direction. That's why all the outside proton is having high ppm, that is 9 ppm, and inside proton is having low ppm, that is minus 3 ppm. Now we'll see in case of an anti-aromatic case. Now we'll see in case of anti-aromatic system. We have seen 12 aniline is anti-aromatic. If you are taking this molecule, there is protons inside the ring, that is these protons, and there is protons outside the ring. These all protons will be outside the ring. So what we have seen for the anti-aromatic, outside proton and inside proton. Outside proton should have low ppm and inside proton should have high ppm. In this case, it is true. The inside proton, due to the anti-aromaticity, it will have ppm around 7.9 ppm. And outside proton, due to the anti-aromaticity, it will have low ppm. It will have around 5.9 ppm. So this is all about the NMR of aromatic and anti-aromatic compound. Now we'll see a few questions in this class and we'll wind up today's class. Okay. So now we'll see a few questions regarding aromaticity. Suppose this molecule is interacting with this molecule. Here, this is an example of base. So what base will do? It will take the most acidic proton in the molecule. So which is the most acidic proton? Here you can see there is an sp3 carbon present here. So if we are adding a base will take the H plus which is presenting on this carbon. And if we are losing an hydrogen which were present on this carbon, what we will get in the product? Suppose we are losing H plus from this carbon, then instead of that H plus, there will be a negative charge in the carbon, right? A negative charge will form in that carbon by losing a proton. Now, if you are looking at this molecule is a cyclic molecule. Now, you may be wondering whether we will consider this pi bond or not. We will consider this pi bond also because in this cyclic system, this carbon is also part of the cyclic system. Here, this pi bond is not isolated pi bond. This is also part of our cyclic system. So, if you are looking, it is cyclic and all carbon atom present is sp2 hybrid. So, it is planar and there is alternate double and single bond. So, it is conjugated. And now we have to count the number of electron which is taken by the delocalization. This 1, 2, 3, 4, 5, 6, 7. Total 7 pi bond, that is total 14 pi electron. So an example of 4n plus 2 system. So this is a aromatic molecule. So this reaction will happen because from non-aromatic, this molecule is changing to aromatic after the reaction. Okay. Now, what will be the product of this reaction? Now, this is a CX bond. This bond will break. And if this bond is breaking, what will happen? This bonding pair will move towards bromine. That is Br minus will form. And we'll get a positive charge here. So that is from this we'll get a Br minus and a positive charge. And this Br minus will react with the Ag plus. So we'll get AgBr. So if we are looking at our product, this molecule, it is a propylene cation. It is aromatic molecule. So this reaction also will happen very readily. Here the question is the rate of SN1 reaction. So what is SN1 reaction? Suppose we have a CX bond in our molecule. There is two ways. Suppose a nucleophile is attacking this carbon. There can be two ways in this reaction is happening. One chance is that the nucleophile is attacking at the same time CX bond is breaking also. In that time, a transition state like this will present. That is, this bond is forming, this bond is breaking. The second chance is that first the CX bond will break, then we'll get a carbocation. In the second step, this carbocation will react with the nucleophile. The second type of reaction that first the CX bond will break and we'll get a carbocation, then the nucleophile react. This type of reaction is called SN1 reaction. Okay. Here the substitution nucleophilic mononuclear. This is the full form of SN1. So in SN1, as of now, you just remember SN1, first step is the bond breaking of C and X bond. So here, the first step is this bond has to break. The bonding electron will go with the fluorine and we'll get Cl minus and a positive charge will come here. And here also, for the SN1 to happen, first step is the breaking of CX bond and this bonding electron will go with the chlorine and you'll get Cl minus and you'll get this. So this is our product. If you are comparing both this and this we already know since sp3 atoms are present, it is a non-aromatic system. But if you are looking here, all atoms are sp2 hybridized. It is cyclic planar conjugated and there is 2 electron. That is an example of 4n+2 system. So this system is aromatic. So comparing non-aromatic and aromatic is the stable one compared to non-aromatic. So we are getting a stable product here. If you are getting a stable product in a reaction, that means that reaction will happen fast. So suppose this is the K1 is the first reaction, K2 is the rate of second reaction, K2 will be higher than K1 because in second reaction we are getting an aromatic product which is a stable product. Okay, so K2 will be greater than K1 in this case. Next question is that which is the most acidic? So acidicity of a molecule determined by the easiness of a molecule to lose a proton. So we will see in each we will lose H plus and we will see the stability of the remaining molecule. Okay. So if this molecule is losing a proton, from where it will lose? It will lose from the sp3 carbon. That is from this carbon it will lose the proton. So if it is losing a proton from this carbon, you will get a negative charge in that carbon. So you'll get a product like this. And from here, if you are losing a proton, we'll get a negative charge in this carbon. So you'll get a product like this. Here, negative charge will form here. And this will happen in all the cases. From wherever we are losing a proton, there a negative charge will form. Okay. In the last case also, here it is the sp3 carbon is present here. So from here only we are losing a proton, a negative charge will come here. Now to see which is more acidic, what we have to determine is which is the most stable one. If we are getting a stable product after losing a proton, that means that reaction will happen fast. That means that will be most acidic. To determine which is the most acidic one, we have to see what molecule will form after losing a proton. Which is more stable, that will be most acidic. Okay. So if we are looking at all of this, here we can see this is example of aromatic. Here it is an example of, we have already seen this is tropylium anion. It is non-aromatic. This again, if you are only looking at this structure here, we can see it is aromatic. And here it is anti-aromatic. We have already seen this structure previously. That's why I am not describing how to find whether it is aromatic or anti-aromatic, because we have already discussed the aromaticity of all these compounds in this class itself. Okay. So now we go to aromatic. This and this both are aromatic. And now we have to compare the stability of this and this. If you are looking here, there is no substituent present on this. This is aromatic. But if you are looking here, this is aromatic plus the CF3 groups is present on the each carbon atom. CF3 group is the group which is having minus I effect. That means this group will attract the electron density towards it. So all of the CF3 group will attract the electron density towards it. So this will stabilize the negative charge. This molecule is only having the aromaticity, but this molecule is having aromaticity plus minus I effect. So this molecule will be most stable. That means this molecule will be most acidic. So in question, if they're asking which molecule is most acidic, what you have to do? You have to lose a proton from the molecule. And after losing a proton, you have to determine which is the most stable structure out of all the structures given. So the most stable structure will be the most acidic one. Okay. So now we'll discuss the last question and we'll wind up today's class. The question is which molecule has the highest dipole moment? And we have given 3 questions. Here, high dipole moment means there should be a charge formation. Here in this molecule, the charge formation means there should be a breaking of pi bond. So in which we'll see in which molecule the pi bond will break easily, and you'll see in which structure after breaking the pi bond we'll get very stable structure. In that molecule only the breaking of pi bond will happen fast and we will get high dipole moment. Okay. So we'll see what will be the product of each cases, first molecule, since it is C double bond O, the breaking of pi bond will only happen towards oxygen because oxygen is the most electronegative element compared to carbon. After this, we'll get a molecule like this. Here, there will be a positive charge on the carbon. In second molecule, again, the pi bond will break like this. And we will get a molecule like this. In third molecule also, after bond breaking, we'll get a molecule like this. If you are looking at each of this product, the first molecule, we know it is anti-aromatic because here only 4 electrons are present. So it is a 4n system. Next, it is an example of tropylium cation. So it is aromatic because here 3 pi bonds, so total 6 electrons. That means 4n plus 2 system is taking part in conjugation. So it is a aromatic molecule. In third case, all these carbons are sp3 hybridized carbon. That means this is an example of non-aromatic. If we are comparing the stability of both aromatic, anti-aromatic, and with non-aromatic, you'll see aromatic is more stable, then non-aromatic, then anti-aromatic. So if you are numbering this, it is 1, 2, and 3. 2 is the most stable one, then comes 3, then comes 1 because anti-aromatic is the least stable structure. If you're comparing both these 3 molecules and these 3 molecules, the first 3 molecules are neutral molecule, zero dipole moment, but this molecule is having dipole moments, but the formation of first molecule from A is least favored because it is anti-aromatic, but the formation of 2 from B is most favored because it is aromatic. So this molecule will form readily. That's why the dipole moment will be highest for compound B. Okay, so with this we have winded up the most important topics of aromaticity. So I hope you all understood what you have taken in this class. So thank you all.